there's points inside and outside the curve. So a curve is a closed set because it is a subset of its boundary. Excuse me, the boundary is a subset of the curve. So a curve is a closed set. But this is not a domain because it's not, obviously it's not an open connected set. And it's also not a region because you can't, it is not the union of a region and the boundary of the region, right? So it's something else. Like a curve is just a closed set. Topology is a rich tapestry. There's so much out there to talk about. But I think that's about all I can tell you for this here. What we move on to now, I think that's it. Oh! Rats. I bet I'm out of time. No, I'm not out of time. Haha. We now enter the lightning round. Let's see here. I am so thirsty. I tell you what. I'm probably gonna go drink a coffee after this, and then I'll be even more thirsty. You know.
Why don't you get water?
I know. It's in my truck. It's boring.
His diet is milk and coffee. Those are the things that I don't drink. You don't drink coffee? I can't have it. Why? Have you ever seen the movie Lately? There's a squirrel and he's twitchy. Oh, you see it twitchy? No, he was given a cat.
He grows a tail. That's what his point was. Like a squirrel. No.
I just kind of love that cat. Okay.
All right. So what I want to tell you in brief is like how do we do limits and all that. So I've been telling you, of course, about the basic notions of topology, and I think we covered pretty much all the terms here. I think I got them all. We just got to here. The next thing was bounded. A subset of the complex plane is bounded if you can fit it inside a disk of some radius. All right, that's a bounded set. If a set is both closed and bounded, it's said to be compact. All right, compact sets are special. This is a theorem that connects topology and calculus a bit. If we have a continuously differentiable function, and by that I mean that the partial derivatives exist and they're continuous themselves, okay? On a domain D, such that the gradient, which is this thing, is 0, then on D, then H is constant. Right? So the proof is involves the things we've talked about so far. Since D is connected, there's a polygonal path between any 2 points, right? And you can, let P1 through Pn be the points at which the line segments meet. And so basically, and we can parameterize these paths such that the domain of the first one is 0 to 1. And so I just look at the first one. So if I take the derivative of H composed with gamma 1, then the chain rule from Calc 3 says it's the gradient of the H composed with gamma 1 dot d gamma 1 dt. But we're given that the gradient's 0, right? So that says that this derivative is constant, which means that H along the points gamma 1 of t can't change. So that shows you that the value of H is the same at the starting point of the first part of the path and the ending point of the first part of the path. But if we can do this for the first segment, we can do it for the second and the third and the fourth, right? And so you get equality of the function at each one of the points that forms the path. But it's a connected region, right? So there's a path between any 2 arbitrary points, which then shows us that H of P is equal to H of Q for any P and Q in the set. So now if the region was not connected, we couldn't form this argument. See, it could be that h has one value on the one part of the separation, and h has a different value on the other part of the separation. Like if the set is disconnected with just two pieces that themselves are connected, on each of the connected subsets, we could apply this argument and have like h equal to a constant on that set, and then h equal to a constant on the other set. But we wouldn't know that they're the same constant unless we can join them by the path. So that's how the topology enters in here, the connectedness. So that's an important thing. We use that sometimes. All right, some more fussy definitions. We say y in C is a limit point of S if every open disk centered at y contains points in S with y removed. All right. We say that y is an isolated point or an exterior point of S if there exist open disks about y which do not contain other points in S. All right. It is kind of what it sounds like an isolated point. You know, take any of my examples and just throw another dot on the marker board on the whiteboard, then that point will be an isolated point. All right. As long as the dot isn't physically connected to the other part of the set. You know. The set of all interior points is called the interior, and the set of all exterior points for S is called exterior. I almost never use this in the course. I don't even know why it's here. The closure of S is defined to be S union with all its limits points. So this is the closure of S. For example, if the double scrolling, it has upon me. So if you take the closure of the open set, open disk, you get the closed disk, for example. So I think of the closure of a set as like the smallest closed set, which also contains the set. That's essentially what closure is. So like here, the open disk, the boundary of the open disk is the circle. All right, and so anyway, oh, by the way, the exterior of a disk is called the outer annulus. We'll look at that later. So it's just some words. This whole lecture is just story time. Like, we're not learning how to solve any problem. We're just learning a bunch of terminology, right? Here, I think, is an attempt at proof of the theorem that polygonal connected is the same as the separation thing. So you can look at that if you're interested in topologies. I don't need to make this apology because I did not spend class time on it. So woohoo! Let's keep that true. Next up, we talk about sequences and limits. So how do you define a sequential limit? Well, the same way you did in calculus. Let an be a complex sequence. We say an goes to a if for each epsilon greater than 0, there exists an n in the natural numbers, such that the distance from a sub n to a is less than epsilon whenever n is greater than big N. In this case, we write the limit as n goes to infinity of a sub n equals to a. So this is how you define a complex sequence, just like you defined sequence in Calc 2, just instead of having absolute value, now we have, you know, modulus. You can talk about a sequence being bounded, all right? It is what it sounds like. It's bounded if you can, you know, have the complex length of the sequence less than some r for all r. Here's your favorite sequential theorems. The sequence of a sum is the limit of a sum is the sum of the limits. The limit of a product of two sequences is the product of the limits of the sequences. Likewise for the quotient. All of your favorite convergent sequence theorems for complex sequences go through just the same. There is no in-between theorem for complex sequences because we don't have any way of ordering complex numbers. Like, is 1 less than I? Is I less than 1? It's a trick question. You can't order the complex numbers in this way. All right. So that's one of the big differences between the real numbers and the complex numbers. Any two real numbers, either one is greater than the other or the other is greater than the one, right? I mean, or they're equal. There's this trichotomy, yeah? Such it's not the case for the complexes. There's no way to do that. But there are other advantages, right? Like the complex numbers are an algebraically closed field. So we have the situation that every polynomial factors, right? So this is just a review of some like inside baseball about sequences. I don't know if we really need all this, but it's here for the sake of completion. That's kind of a joke. The joke is upcoming. A complex sequence converges if and only if the real and the imaginary part separately converge as real sequences. That's one of the things that's proved right here. Another definition, we say a sequence is Cauchy if, for every epsilon greater than 0, if you go far enough out in the sequence, you can make the difference between elements of the sequence as small as you like. This is a Cauchy sequence, right? And double scrolling upon me again. Ah. A space is complete, that was the joke, if every Cauchy sequence converges. So you can prove that the real numbers are complete. So like an example of a Cauchy sequence which doesn't converge, just so you understand a little bit better, if you take the digits in the square root of 2. So like the sequence here is the following, like 1, and then 1.4, 1.41, 1.414. All of those truncated decimals are rational numbers, right? So the truncated decimal expansion of the square root of 2 is a rational sequence. All right, and you can prove it's Cauchy because if you go far enough out, the difference between truncated decimal expansions of the square root of 2 can be made arbitrarily small by going arbitrarily far out. Right, so it is a Cauchy sequence, and yet the limit of that sequence is the square root of 2. And if you're taking Math 200, you probably proved that the square root of 2 is not a rational number. If you haven't yet, you will. Or if you're not taking Math 200 because you're an engineer. Sorry, what's that?
I am taking it.
Okay, phew. Okay, phew. But communicate to your engineering brethren that it wasn't necessary for this class, really. It really didn't help at all, hardly, to speak of. So yes, a complex sequence, so Cauchy numbers are complete. I did start class 2 minutes late, so I'm going to end it 2 minutes late. So now, next up, we define the limit of a function. So if for each epsilon greater than 0, there exists delta greater than 0, such that whenever you're within delta units of z naught, not including z naught, see this 0 here, you can make the modulus the length of f of z minus L less than epsilon. This is exactly the definition of limit we gave in Calculus 1, except instead of absolute value, we now have magnitude. All right? And all of the same proofs go through. The limit of the sum is the sum of the limits. The limit of the product is the product of the limits. The quotient rule goes through. All of your limit laws are the same as what you learned in Calculus 3. And it is a multivariate limit. So it is not nice. Like you can have nefarious things. You can't, if you have path limits going into a point, like you got this limit exists, this limit exists, this limit exists, this limit exists, and they're all equal, it still can be the case that that multivariate two-variable limit in the real sense doesn't exist. Because the two-dimensional limit is a two-dimensional thing. One-dimensional data won't pin it down. It's just how it is, without some sort of continuity condition. So anyway, I just wanted to tell you, we have all our limit laws. I don't want to prove these in here because they're not that they are interesting, but they're not for this class. A function's continuous if it's equal to its limit, right? Like limit of z goes to z naught of f of z is equal to f of z naught. That makes f continuous at z naught. All right? And there is a connection between the epsilon delta definition of limit and the sequential definition of limit. Like you can capture continuity at a point either by the epsilon delta thing, or you can use that whenever you feed it a sequence, it produces a sequence which likewise converges. The so-called sequential definition. So, anything else to tell you in here? The limit is unique. The limit of z as z approaches a is a. The limit as z approaches a of a constant is a constant. I'm not telling you anything here that's terribly, like I said, the sum law works. You pull a constant out. You can extend it to finite sums. The product rule works, but you've never seen this proved. This is technical. The product rule for limits is uglier than what you saw in Calculus 1. Nobody did this in Calculus 1. See that? Nobody did this. And so what I'm trying to tell you is, in short, all of our favorite limits go through. And I'm sorry I have shortchanged that part of the material, but I will now have to go look at your mission 2 and find out whether or not I have to give additional lecture in order to make up for what I've just kind of glossed over. Because I want to make sure that we have lots of time to understand chapter 4, all right? Because that's really where the difference between real analysis and complex analysis starts to appear. Basically, all I'm saying in this chapter is that the limits over the complex number system are just limits over the plane that you already know from Calculus 3. It's just a new notation, really. So, I shut up.